Hello everyone. So welcome back to our latest lecture session. So in the previous session we introduced ourselves to aqueous complexes and looked at why they are relevant, or we have been discussing that, and let's take that discussion further. Right, we are discussing the importance of aqueous complexes, right, and in that context we discussed that the toxicity is going to be affected, right, as in now you, instead of just having the free metal at relatively high concentration, if you add a ligand you are going to have both the free metal and the complexes, right. And let us say in general, if let us say only the free metal is what is toxic, and in general let us say if and this is a decent assumption, if the complexes are not toxic, what would that mean for your particular system? That the toxicity of your particular system is decreasing, right. So that is what we can look at that. And the second case is with respect to solubility. Let us say for example, you might have noticed in either your freshman chemistry practical class or such, you take a solution, you keep adding some salts or such. At a certain point you are going to see residue or precipitation at the bottom of your beaker or such, let us say, right, or the sides, let us say, depending on the kind of solution you are using, right. So let us say you want to increase, let us say, the concentration of some particular metal, let us say not a heavy metal that is toxic, but let us say some metal that is useful to you, let us say. You want to increase the concentration of some metal in your particular solution, but beyond a threshold you know that it can precipitate out, right. So what can you do? You can add a ligand, right, so that the total metal concentration is going to be higher. Without the ligand, let us say, it is just going to, let us say, stay as either the free metal or form precipitate and settle down, or form precipitate and go change into the solid phase. But let us say that is not what I want. I want it to stay in solution. So what can I do now? So I can increase the concentration of the total metal, keep that in mind, by adding the ligand, right. Ligands, as you know, are more the complexes, as you know, are more soluble, right, or soluble species. So that would in effect mean you can increase the total concentration of the metal by adding ligands and forming your aqueous complexes. So when you want to adjust the pardon me, what is this now, the solubility of the particular metal, that is something that you can take into account. The third aspect is sorbability, let us see. Right. So let us say the sorption or adsorption, let us say it depends on the relative sorbability of the metal, let us say. So let us say if you want to either increase or decrease the sorbability, you can then consider the addition of ligands to form complexes. For example, let us say if you want to increase the sorbability, right, and let us say you know that your complex is relatively more sorbable, right, let us say the charge is such that it favors sorption. So maybe then let us say you are going to add the ligand so that you have more complexes, and that can increase your efficiency, not efficiency, I guess, the sorbability of your particular system. Why is that? Because in this particular case or that particular scenario that you are considering, the sorbability of your particular complex is higher. But obviously keep in mind it depends on the scenario that you are looking at. Obviously most of them look at charge, right, or charge plays an important role. So let us say if you want to decrease the sorbability, and in a different case let us say the sorbability of your complex is relatively low, right, then by adding the ligand and forming the complex you can decrease the sorbability of your particular metal, right. So again depending on the relative sorbability of your complexes, you can either increase or decrease the sorbability of your particular metals. That is one particular aspect. So three major applications: one is toxicity, right, one is solubility, another is sorbability, right. So in general now let us move on to some of the examples that you might have come across, at least in the lab, So this is something that we can look at. So when we are trying to measure hardness, right, hardness, and I think you are trying to measure Ca2 plus and Mg2 plus, right. So how do you go about that? If people can recall that, or I can help refresh their memories, you add EBT, right, that is again a ligand, eriochrome black T indicator, right, EBT, right, you add that initially, right, and then you start, I believe, titrating with EDTA, right, until I believe a blue color appears, right. the blue color is your end point, if you remember that, I guess. So what's happening here, right? So here initially, again I said EBT is a ligand and also EDTA2 is a ligand. So Mg EBT complexes are formed initially, okay. Magnesium and EBT complexes are formed when you initially add EBT to your solution, right. So then you are titrating with EDTA, right. So that in general leads to formation of a more stronger or stable complex, the Mg EDTA complex, right. So the ligand is replaced here, earlier the complex was between magnesium and EBT, now with the addition of EDTA, as you are titrating your solution with EDTA, you are now going to end up with what is this now, Mg EDTA complex. So when all the Mg EBT is replaced by or the EBT is replaced by EDTA in your Mg EBT complex, that is when you end up with your blue color, right, and that is the end point that you observe. So again that is one particular illustration of where it is one of your practical applications of your particular complexes, right. So again complexes, they are again ever present in most of your titrations. So before we move further though, one other aspect, so in your COD test, right, you might have seen that you add mercury, right, if you would have paid attention to your test. So why is that though, if you think about that, that is because you want to what do we say, take care of the interferences due to Cl minus. As in what is your COD test, you are adding a strong oxidizing agent and potassium dichromate, I guess, right, or dichromate, and that can oxidize Cl minus, right. So that can lead to overestimation of your COD, yes. So you want to remove the interference due to this Cl minus, as in Cl minus, right, can be oxidized by what is this now, your potassium dichromate, right, yes, but you want to remove this particular interference. So that is why you add mercury, right. So the complexes are formed between Hg2 plus and Cl minus, thus you are now removing the interference from Cl minus on your COD test, otherwise the Cl minus can be oxidized to the various forms of oxide forms of Cl, right. So that is obviously another example of why you would add or practical example of your complexes. So now we move on to the next aspect. We need to now decide, am I going to look at kinetics, right, or am I going to consider equilibrium, right, or do I need to consider both the aspects, right. So in general acids and bases, we mentioned that the relevant half reaction lifetimes are, right, half lives are of the order of milliseconds, right. So in this case they are not as fast, but they are still pretty fast. They are, let us say, in general order of, let us say, a few seconds to minutes. So in general they are still, for most practical purposes, they are relatively fast, right. So seconds to minutes, unlike acids and bases, they do take more time, right, or the relevant reactions are relatively slower compared to acids and bases, but for most practical purposes, the formation of your particular complexes are relatively fast, right. So thus you can consider that for most of the systems that you see, kinetics do not play an important role. Why is that? Because they are so fast that you more or less mostly end up with equilibrium, right. So again, similar to acids and bases, now we are going to discuss equilibrium in much greater detail, right. Again, why is that? Because the kinetics are in general relatively fast enough such that they end up reaching, or the system ends up reaching the equilibrium, right. So here now the major aspect is they are relatively fast, and that is why we are going to look at equilibrium, or we achieve equilibrium usually, and that is why we are going to discuss equilibrium now, right. So equilibrium, I guess, before we go further, if people looked at the relevant textbooks, I think Stum and Morgan, right, water chemistry by Mark M. Benjamin, and aquatic chemistry, I believe, by Brezonic and Arnold, or any other book, let us say, when you are discussing complexes, right, you would have different kinds of coefficients here. If you remember, equilibrium coefficients is one concept we looked at, right. What is an equilibrium coefficient now? If you remember that EA plus B goes to, let us say, C plus D, right, and we mentioned that equilibrium coefficient, this is going to be at equilibrium, I guess, right, activity of C raised to stoichiometry of C, activity of D raised to the stoichiometry of D by activity of A, rise to stoichiometry of A, activity of B, rise to stoichiometry of B, and which we usually approximate by concentration of C, concentration of D by concentration of A, concentration of B, right. This is something we might have discussed or we did discuss in acids and bases and in equilibrium and so on, right. But here though we have different ways of different types of coefficients depending on, you know, is the ligand and or the ligand and metal, you know, going from one step or two step, right, or is it, let us say, protonated ligand or deprotonated ligand. Anyway, let me write that down and hopefully it is going to be more clearer here. So in equilibrium we are going to talk about coefficients, right. So we have different cases. One is stepwise, right, and another case would be direct, okay. And in this case of stepwise, right, I am going to have a deprotonated ligand, and for that the coefficient is going to be expressed as Ki, please keep that in mind, right. And the other case is when I have a protonated ligand, pardon me, and that I am going to represent by Ki star. And if I am assuming it is a direct reaction, again which I am going to, you know, explain further, keep in mind that there are different coefficients here when we are talking about equilibrium for complexes, one for stepwise, one set for stepwise, one for direct, one for protonated ligand, one for deprotonated ligand, I guess. Anyway, stepwise, again here too we have what do we have here, let us say I will call this 1 deprotonated ligand, and that is going to be beta here, and here let us say if it is protonated ligand it is going to be beta I star. Anyway, different coefficients would be available in different books, so you just need to be aware of what it is. Let us say if a book says it is beta star, let us say, what is it that you are referring to, or which reaction are you referring to, or which complex are you referring to. The complex might be such that it depends upon the relevant products, and that you can glean from the relevant coefficients. So let us look at the example. So stepwise, so the first aspect we are going to look at is stepwise and deprotonated ligand. So you know, stepwise obviously it makes sense, it is self-explanatory. Let us say charge of the metal M is Z and L is minus X, let us say, right, and that can form a complex MLZ minus X, right. And an example will be Al3 plus is my metal, let us say, and it is going to react with the deprotonated ligand OH minus, and it can form Al OH, and the charge is now going to be 2 plus, right. This is one complex. So again stepwise, right. So again I need to go from MLZ minus X plus another ligand L minus X, it is now going to be equal to ML, let us say 2 and Z minus 2X, right. Again this is the generic form, you know, it is obviously flexible depending upon how you write the coefficients or such. So what does that mean? So here it is going to be Al OH 2 plus charge plus OH minus, again stepwise, right, it is stepwise. Al3 plus first forms AlOH 2 plus, and AlOH 2 plus again reacts with, not reacts, let us say, okay, reacts with the deprotonated ligand OH minus to form Al OH twice and plus 1 charge, I guess, right. And again the next aspect will be again similarly ML2 Z minus 2X plus L minus X can go to ML3 Z minus 3X, and an example here would then be now Al OH twice plus OH minus, right, would then go to Al OH thrice 0 charge, right. So again stepwise, so here you will have K1 coefficient for this, K2 and K3, right, K1, K2 and K3, right. So here you have metal and you have a ligand. So here when you talk about coefficients in terms of equilibrium coefficients in terms of just K, what does it mean? Al3 plus going to Al and reacting with OH minus and going to Al OH 2 plus charge and then stepwise addition one after the other. So obviously if it is a protonated ligand, still stepwise, and now we are going to talk about protonated ligand. So again that's self explanatory, I guess, right? So it's M plus Z H L, I mean the charges, I guess, on L going to be minus X. So just keep that in mind, that it's an approximation here that we are writing a generic form. It's going to be M L Z minus X plus H plus, right? And the coefficient here is going to be K1 star, right? And what does that mean? Let's write that down. It's going to be equal to Al3 plus, and what's the protonated ligand here? Protonated means OH minus has a proton, right? It's H2O, and now it can go to Al OH 2 plus charge plus H plus, right? So for this we have K1 star. I am not going to write the generic form further, but I will just write this further. So I can now say stepwise the next example here will be Al OH 2 plus the protonated ligand, it's protonated ligand, right, plus H2O can go to Al OH twice plus charge plus H plus, and what's the coefficient here? It's going to be K2 star. So someone talks about K2 star, right? K2 star or K1 star, they are talking about the protonated form of the ligand, you know, forming a complex with the metal, right? So the last set would now be Al OH twice plus the protonated ligand, which is H2O, right, would go to Al OH thrice no charge plus H plus, and that's going to be equal to K3 star, right. So obviously it's self explanatory once you understand one aspect, right. Now we are going to move on to the second aspect, which is the deprotonated ligand, but the direct addition, I guess. Again it's self explanatory, so let's see what it is that we are up to here. So now I am moving on to the direct addition. Here I looked at stepwise addition as in one complex and then addition of only one ligand to that complex, again one complex, another addition of one ligand. But here it's obviously going to be a direct addition. So let's look at what that is, I guess, right. So the first example is going to be similar, right. M plus Z plus L minus X is going to be equal to M L Z minus X. So the coefficient is going to be beta 1, right. Again the example is let us say similar here, and I will write that down. Al3 plus OH minus goes to Al OH 2 plus. But let us say for the next case, let us say the formation of the next complex, it is not stepwise anymore, now it is direct addition as in Al3 plus 2 OH minus goes over to form or forms Al OH twice plus charge, right, a direct addition, right. Earlier we had only one stepwise, but now we have a direct addition, and same case for the next particular complex Al3 plus 3 OH minus will directly form Al OH thrice, right. So again the key is that, you know, we now have a direct addition of the, or we are considering what do we say, that there is a direct addition of the ligand, again beta 1, beta 2 and beta 3, right. So generic form, maybe if I can write that down, M plus Z plus 2 L minus X would go to M L2 Z minus 2X, right. Again direct addition, right, what is the generic form? M charge is plus Z, let us say 3 L minus X would go to M L3 and Z minus 3X. Anyway, generic forms you can play around with it to get a form that suits you better, but again here we are talking about direct addition of the ligand, right, to form the relevant complex, unlike earlier where we just talked about a single step addition. So one complex will then lead to the formation of the other complex and so on. So let us obviously again write down the protonated ligand. So that is again self explanatory. I will start with my example, I guess, right. So it is Al3 plus what is it now, H2O will form what now? Al OH 2 plus H plus, and what's the coefficient here? It's going to be beta 1 star, right? I'm doing away with the generic form. And here again it's the protonated ligand, that's the key here. It's the protonated ligand and direct addition. So the next complex 2 can be formed from direct addition. What is that, or how is that? I guess that's going to be equal to 2H2O, right? And that's again going to form Al OH twice and plus charge plus 2H plus, right? And again Al3 plus 3H2O will form Al OH thrice no charge plus 3H plus, and obviously the coefficients are going to now be beta 2 star and beta 3 star, right? Again, it might seem a bit confusing, but it's just a combination of two aspects. One is when we have stepwise, and one is when we have stepwise and direct, and the other is when we have protonated and deprotonated ligands, right? So different books have different coefficients, so you should be able to understand what's what, and go from there, but there, I guess, right? So again, one other aspect that you need to consider is when you solve for the equilibrium, right, you usually choose components. So when you choose components, if you choose in such a way and the relevant coefficients in such a way, it can simplify your particular solution further. But if you choose coefficients, anyway, we'll have an example later, I guess, depending on your choice of what do we say coefficients, you can either end up with a very complex calculation or a relatively simple calculation, right? So let's say in general, I think the protonated ligand with the direct step is the most easiest way to solve for what do we say different equilibrium solutions and such. So let's look at, I believe, one example here, right? Anyway, before I go for examples, I guess I need to talk about the strength of complexes. Right. So two generic cases, let's say A and B. So one is, let's say, multidentate, right, when you have more than one electron or more than one binding site, right? Those complexes multidentate are usually stronger than monodentate, right? So that's one aspect. So multidentate are usually more stronger than monodentate, right? And B would be when, let's say, you have multiple charges rather than, let's say, charge single charge or double charge. Let's say you have charge of +3 or -3 on your metal or ligand. So the greater the charge on either your metal or ligand, let's say, the strength of your complex would increase, right? So that's one particular case, I guess. So in other cases, when you are going to look at the hydrated radius, right? So that's the case when, let's say, this might you might have come across when you looked at ion exchange process. So that's something we are going to discuss again in detail. So in this context, we need to look at also individual metal ligand interactions, right? As in different kinds of metals would form, let's say, a stronger complex with one kind of a ligand, but what do we say, not as strong with different another ligand. We are going to look at those particular cases here. So here I am going to come across, let's say, two cases here. One is the A metals or hard acids, I guess, right? So in general, what am I talking about? I am talking about Na, K, Mg, Ca, Al, Cr and Fe, right? So these in general are referred to as, what is this now, hard acids, and they usually end up forming ionic bonds, I guess, with the during the relevant complexation, right? So let's look at their particular preference, I guess. So the ligand preference. So they would prefer F greater than oxygen, or the strength of the complex anyway would be greater in this order. Right, and usually they form And obviously the second aspect would be, right, and here we looked at A metals or hard acids. So then we are going to look at B metals or soft acids, right. And what are we referring to? We are referring to Ag, Cd, Zn, Hg, Pb, and mercury, lead, zinc, cadmium, silver, right. And the ligand preference in this case is usually the opposite, I guess, right. And here it is going to be such that they prefer to form complexes with sulfur, iodine, Br, Cl, nitrogen, oxygen, and fluorine or F minus, I guess, right. So here we looked at two cases, right. One is we defined or not defined, I guess this is common knowledge. We have hard acids and soft acids or A metals and B metals, right. So we looked at what is it now, sodium, magnesium, calcium, aluminum, and so on. So they have a particular preference for the ligands, and that is something that we listed as an F greater than O, nitrogen, bromine, iodine, and sulfur, right. But if it is the B metals, usually it is the reverse order. They would form stronger complexes with sulfur than with let us say oxygen, right. So this is something for you to keep in mind. So in general, what are the aspects? They are the strength of the complex are depend upon, as in multidentate is greater than monodentate, right. So that is something we just talked about. In general, if the charge on either the metal or ligand is greater greater than 1, right. The higher the charge, the better the or the greater the strength of the complex, right. And then we also talked about the hydrated ionic radius, right, and that is something we need to consider. And then we talked about the ligand preference for A metals and B metals, right. So now let us go on to looking at what is this now, equilibrium models, right. Again, you do not need to mug these up, but the key is that for you to be able to understand, develop that intuition, I guess, right. For example, as easily as which acid is, let us say, a stronger acid or a weaker acid, you should, let us say, at the end of the course be able to understand, which complexes are relatively more stable or which are more stronger, let us say, right. Ionic radii, so it has a concentrated charge, let us say, right. The smaller the ionic radii, thus the greater or the stronger the complex. And again, that is something you would come across in ion exchange process too. Or obviously if the greater the charge, the greater the complex, and that is something that is logical too. But with respect to A metals or B metals, obviously there is a preference here. So now equilibrium metals, equilibrium models, pardon me, and how do we go about that? Again, this is similar to what we talked about. Everything with respect to equilibrium models we can solve by getting it done with respect to component balance, right. Again, component, you define components, right, or you first identify the species, then define the components, right, get in the tableau, write the total component concentrations, right, and then solve for the relevant what do we say, variables. So let us look at one example here that I have, right, and I think we are going to look at Al3 plus, right, or complexes of aluminum, I guess, right. So how do I go about this now? So first I need to identify the species, right, and what are the species here? So first it is always going to be H plus and OH minus, right, and then the free metal, and then you are going to list all the different complexes. So let us say initially you are not sure, you can look at some of the books that you have and list the complexes based on the number of coefficients that are listed, right. So for aluminum you are usually going to have 4 relevant complexes. So let us list them, let us say. So let us say we are just looking at it, our solutions in water, right. So I am going to have H plus and OH minus, and then Al3 plus, and the other, after addition of one particular ligand, AlOH2 plus and AlOH twice, right, with plus 1 charge. This is twice, and then AlOH thrice, no charge, and AlOH4 with a negative charge. Again, if you look at the relevant books or look up the relevant coefficients, you would see that for aluminum you would have 4 coefficients listed. So from that you can understand that more or less there are 4 complexes that are usually predominant for aluminum, right? And depending upon the type of what do we say, coefficients listed, as in beta 1 star or so on, you can then try to approximate what they are also, I guess, right? So we are done with that. So now I need to come up with my particular components, right? And obviously again similar to acids and bases, right? What do we choose? We are going to choose building blocks, right, based upon the simplest combination, right, and simplest and smallest combination of components. You should be able to build all the other species. What are species? They are actual compounds present in equilibrium in the solution, but components, they do not need to be so, but they are just building blocks that you are going to use to form your species, right. So obviously you know always going to have H plus, and what else is the building block here? Obviously as you see it is going to be Al3 plus, right. So that is what you have here. So usually you choose the metal and the what do we say, H plus, and in this case the ligand is OH minus, so you do not need to choose any other ligand here. You can get by with just choosing H plus, because you can get to OH minus by subtracting H plus from H2O, right. So thus you do not need to choose any other ligand, but let us say there was some other ligand, you need to choose that ligand as one of your components, right. So what next now, right? You need to form your equations or the formation equations. So the formation equations. So what are they about? Obviously as we discussed earlier, so each species need to be formed from a combination of these particular components. So I am going to have my particular what do we say, species listed here, H plus, OH minus, and Al3 plus, Al OH2 plus, right, and Al OH twice plus Al OH thrice, no charge, Al OH for negative charge, right. So now I need to form these particular species from my 4 components. So one H plus is H plus, and H2O minus H plus. H2O is always a component, right. H2O minus H plus is OH minus. Al3 plus will form Al3 plus, and how do I end up with AlOH twice here? Let us say I can write it in different forms. So let us say I can write it as Al3 plus H2O will lead to AlOH twice plus H plus, right. This is something we know. Or I can say here it is going to be minus H plus Al3 plus H2O goes to AlOH 2 plus, right. So next case here, this particular species, how can I form them? Obviously same case. So it is Al3 plus 2H2O minus 2H plus, right, plus 2H2O minus 2H plus, and how can I form this? It is Al3 plus 3H2O minus 3H plus, right, and again Al3 plus 4H2O minus 4H plus, right. And now I can go ahead and get done with my tableau, right, and here I am going to list all the components here, and my 2 components are, in this case I only have 2 components, Al and 3 plus, H plus and Al3 plus, pardon me, and then I am going to list all the species as different rows, H plus, OH minus, Al3 plus, AlOH 2 plus charge, AlOH twice plus 1 charge, AlOH thrice, and AlOH for 1 negative charge, right. So from these formation equations I can obviously come up with my particular tableau, right. So 1 and 0, that is what I see here, and here again it is minus 1, obviously because H plus has a minus 1 coefficient here, and 0, and here it is going to be, again how did we come up with OH minus? Look at the relevant formation equation. To form one OH minus you need minus 1 of H plus, right, and that is why I plug that in here. And do you need any Al3 plus to form OH minus? None, so that is why we have 0. and this is something we covered earlier too, right. And for Al3 plus you need 0 H plus and 1 Al3 plus. How are you forming AlOH2 plus? How are you forming AlOH2 plus? You need 1 Al3 plus, that is what I am going to write here, and you need minus 1 H plus, right. So similarly for all the other cases, how can I form AlOH2? I need 1 Al3 plus and 2 or minus 2 H plus. And how do I form AlOH thrice? 1 and minus 3, 1 and minus 4, right. So from this, let us say, I can now write my total component balance equations, right. So what are these total component balance equations here? We just have two components here, it is going to be H total and Al total. So let me write that down here rather than the next slide, so that we understand that further. So I will write that Al total, right, is going to be present as, so this is nothing but the sum of this particular set of concentrations here is going to be present as Al3 plus free metal plus concentration of AlOH2 plus, right, plus concentration of AlOH twice plus AlOH thrice 0 charge plus AlOH 4 negative charge, right. Again, where did we get this particular equation from? From this particular tableau or the component balance, right. So similarly now we are going to have H total, right. I am going to write that in the next particular slide, I guess, right. So H total, what is that equal to? It is equal to H plus concentration, right, minus OH minus concentration, right, and I think nothing for Al3 plus, and let me just write down all the complexes so that I do not need to go or jump back and forth. AlOH, AlOH twice with a negative charge, right, and AlOH thrice with no charge, and AlOH 4 with a negative charge, right. And obviously the coefficients, if you remember what they were minus 1 here, minus 2 here, minus 3 here, and minus 4 here. Let us go back and check that. So that is what you see here, minus 1 for AlOH2 plus, you need minus 2 H plus for forming AlOH2 plus, minus 3 and so on, and that is what I plugged in here. H total is nothing but H total equal to H plus minus OH minus and minus 1 times this, minus 2 times this, and so on, right. And again, where did we get that from? From our total component balance equation. Similarly, we had Al total was equal to Al3 plus AlOH2 plus, I am just writing this in so that we can compare them here, I guess, right. AlOH thrice 0, so I messed 1 here, AlOH twice with a positive charge and AlOH 4 with a negative charge, right. So again, how will this component balance help us? It is because let us say you know that the total aluminum is always going to be constant, I mean other than unless you change the scenario, right. So depending on pH, let us say, or such, will total aluminum or Al total change? This will not change. Why is that? The individual concentrations of these variables will change, as in this can increase, others can decrease, and so on, or this can decrease and the others can increase, and so on, right. But the total aluminum or the total component concentration is going to change, and that is the key. I was just trying to refresh your memory. So based on this, you have different applications. So I guess we will look at that particular applications in the, or those applications in our next lecture session, and be done with our complexes, and then move on to the next aspect, which is precipitation and dissolution, right. And thank you, that is it for me for now.